So let's start with data types. So as you know, all MPI communication functions take parameters of the type buff, count, and data type. So everything is expressed in terms of a count of some data type. And if you have used MPI, you've already used this parameter, and you've typically passed it as the MPI, one of the basic types, MPI int or MPI float or MPI real or whatever. But MPI also allows you to do non-contiguous, to send non-contiguous data. So let's say you have an array of data and you want to send bits and pieces of this array. You can send all of it with a single MPI send or receive by constructing a data type. It's called a derived data type to specify this data layout, and similarly receive it on the other side with a single function describing this non-contiguous data layout. So for that purpose, MPI has data type constructor functions. How do you specify this non-contiguous layout? And that's what we'll see. So here's an example. Let's say you have this array where you want to send the green and the blue parts of the array. So that's a strange pattern. So without data types, how you would do it is, and people do that quite commonly, is you somehow copy all of that. You allocate another array, and then copy all of that contiguously into that array, and then send it, and do the same on the receive side. That is, receive it contiguously, and then unpack it in some way, copy it back into your array. So that's somewhat inefficient, because on some networks you can send data directly like this. You don't need to pack it into a contiguous buffer. And the way you pack it yourself by hand may not be the most efficient way of packing it, even on networks that need packing or need communication of a contiguous buffer. So to avoid all that and to let the MPI implementation do this work for you and potentially do it with better performance, you can create derived data types. So the way you would create a derived data type, and we'll see how that is done, is you will create a contiguous data type to describe this. You will create an indexed data type to describe this kind of layout. And then you would create a vector type of these contiguous types, these three contiguous types. And then finally, you would create a struct type of these two different types. And using that struct type as the data type parameter to the send, you can just send it with a single function. So it looks a little complicated, but it's actually just detail. Once you get the idea, just calling these functions is easy. It's not difficult. Okay. So as I said, so this slide just says that why does MPI even have basic data types? Why do you have a buff count data type instead of just sending data in bytes? And if you look at the way communication is done in some other libraries, like the basic socket communication or other things, you just send bytes. Even if you have an integer array, you'll multiply it by size of int and send it out as bytes. But MPI tends to discourage that. And one reason for that is, let's say you're on a heterogeneous system. That is, you are running on a cluster where some of the machines have different architectures. One might be an Intel-based thing, another might be a Spark-based thing or something, and they have different byte orderings. So an integer on one is not the same as an integer on the other because the byte orderings are different. So if you just send it as bytes, you have lost that information that it's actually an array of integers. So it won't make sense on the other side. Whereas an MPI implementation running across this knows that these are two different systems with different byte orderings, and it can internally do the reordering of bytes, so your array is again makes sense on the other side. So that was the basic reason. And MPI has all the language types in there. So the C language. So when you're writing a C program and you have declared a variable as some type, you should use that as the type in the data type argument. So in C99, there are so many types, int 32, int 64. There are lots of new types that you may not know. You may know just the basic C types, but all of them are supported in MPI. And similarly, all the Fortran types are also supported in MPI. So if you're using an integer in Fortran, you have to pass MPI integer, all caps, MPI underscore integer as the type. In C, when you declare an int, a variable as an int, the type you use is MPI underscore int. So MPI underscore int is the C integer type, and MPI underscore integer is the Fortran integer type. And so you have to take care and pass the right type. Let's look at the data type constructor functions. So the simplest, so we'll start with the simplest and move to the more complicated ones. So the simplest is to create a contiguous type. So what this function takes is MPI type contiguous. Let's say you want to create a contiguous type like this. So the first parameter is count, which is the number of types in this. So how much is this? 7. So this would be 7. The next is the type. Each of these count items, whatever type they are. So in this case, let's assume that they are some basic type. Let's say it's an MPI int. So you would pass MPI int. And what you get out of this, the returned type, is a contiguous type that represents this. Now, you cannot directly use this returned type in a send function. You have to call one more function. It's called MPI type commit, and we'll see that later. So you can take the contiguous type and build other complex types out of it, which we will see. But at the end of it, when you're done creating your data types, before you use it in MPI, you have to call another function called MPI type commit. What it does is it allows the MPI implementation to sort of analyze what is this data type, what have you specified, so that later on, when you actually call the communication functions, it doesn't need to do that analysis during the communication, because that can cost some in performance. So it can do it once beforehand at that commit step. Let's say you created a strided pattern, which is like a vector. It can understand that. It can realize that that's what you've done, and it can do some things efficiently. But all that is done at the commit step, internally stored, and then your send receives can happen quickly. So there's one more function to be called, which we will see later. And as I said, you can, the contiguous, in this case, the basic type itself was a simple type, so everything is contiguous. But the type that you pass to MPI contiguous could be anything. So you could have created another derived data type, called a struct type, which we will see. So let's say these set of elements constitute this struct type, and then you can create a contiguous type out of this struct type, which is basically this pattern. It doesn't look contiguous because that struct is replicated, but it is. So what contiguous does is it just takes count copies of this old type and sort of concatenates them together, similar to the way an MPI send would do. Now, what does an MPI send do? When you take a buff count and data type, it takes count copies of this data type starting from this address and then sends them out, right? So that's effectively a contiguous type. So in practice, you don't really need to use this contiguous type. If you're doing this kind of communication, there's no need to create a contiguous type, because that's what MPI send does by itself, right? So you could, all you needed to do is send this data, you could just call MPI send with buff address pointing to this first location, the count as 7, and the data type as MPI int, and that would effectively be you're sending a contiguous type of that type. Where it is useful is where you need to build something beyond that. So it's what you're doing is more than contiguous. So it's a building block for something else, like this. So if you had to send something complicated like this, you could do a struct and then a contiguous of the struct. Is this simple one clear? Yeah.
For the second case, when you send it using MPI, it will send all these blocks?
It will send only the green blocks, whatever is marked as green.
All of them together.
All of them together. It won't send the white stuff, which you don't want to send anyway. Yeah?
In the second case, you can just do an MPI send on the struct with
Yes, you could do that as well. Yeah, because it'll send that.
Yes.
That's why I say contiguous is if your contiguous is the last type that you've created, you don't need it because the send is defined as the same as contiguous. And someone there, yeah.
So in the point-to-point UV code that you have here in the mLife thing, you're using a type vector.
Yeah.
Significant difference between the vector.
Yeah, that's on the next slide. That's on the next slide. And there's a hands-on exercise related to exactly the UV stuff that you mentioned. So we'll come to that as well. Yeah.
What's the difference between this and then declaring part of your memory available for someone else to just read out these specific sections? Why send different sections versus making it open?
Well, even if you make it available for someone to read, how is that person going to read, right? If you're referring to the one-sided operations, even there is a data type parameter because that process is going to call an MPI get, say, which is a one-sided read. But again, how is it going to specify that I want these green ones and not the white ones in between? So that get also takes a buff count data type as a parameter. And that data type would be something that process constructed that describes this layout. Okay? So this is the simplest one. And as someone said, what about vector? So the next one will be vector. And the difference here is now you have blocks of data that are at a regular stride. I mean, it's a constant stride between the blocks. So this is the case. You have these two blocks, then a gap of 1, and then 2, and a gap of 1. So there's a regular stride, a stride that is not changing in this pattern. So that's called a vector type and MPI. And the way you specify this is, again, there is a count, which is the number of these blocks that you want to create the vector type out of. The block length is the number of these blocks in each of these bars. I'm not using the right term, but so the block length would be 2 here. So each of these has a block size of 2. The count is 3 because we have 3 of these. And the stride is the distance between the starting part of the second block and the starting of the first block. So in this case, the stride is 3. There's a gap of 3 between the first element in the second block and the first element in the first block. And the stride is in terms of the size of the old type. So you just say 3, not 3 into size of int. It is 3 units of this old type. So there are 3, effectively, if these were integers and you pass MPI int as this type, then this stride would be 3 MPI integers. Block length is 2, and count is again 3 because we have 3 out here. And what comes out of it is, this MPI data type is an opaque object. So that doesn't make sense to you. You don't need to look at what it is. It is something that only MPI understands. But what it represents or encapsulates is a vector type. And this is quite useful because you often have some strided elements. If you're sending a column of a matrix that is in row major order, that becomes like a vector. So you can build a vector type describing that. And you can also build a complex, complicated vector type where each of the basic elements itself is something more complicated than this, like a struct. So you can recursively call other types. So is a vector type clear? It's just one step after contiguous. The next one is similar to vector, but it covers the case where this gap may not be uniform in this pattern. So if you don't have a constant stride, then you cannot concisely represent it by a single integer. You need a vector there to indicate that stride. So this is the before that, there's h vector. And the h vector, the only difference is it is a vector, but the stride is not in terms of units of the data type. It is the actual data, the stride times the size of int. So it's just a detail which we can ignore for now. Let's look at the indexed one. So the indexed one is a vector. It's like a vector with a non-uniform stride. So let's say you have this kind of pattern where there's a gap of 2 here, 1 here, 2, 3, 2. It's not It's not uniform. So now you cannot have a single stride parameter. So what you now have is an array of displacements. So now each of these has to be specified separately in this array. The rest is the same. You have a count, which is the number of these green bars. So that would be 6 out here. The array of block lengths is, so this is another thing that could be different, as that each of these blocks could be of different sizes. So again, this is of size 1, this is of size 1, this is 2, 1, 2, 1, and so forth. So that's the other thing that is different. The vector had, again, a uniform block size as well. So this becomes an array, this becomes an array. The displacements, again, are what is the displacement from the start of this and the start of the first one, and similarly the start of this and the start of the second one. All that is passed as an array. And then you pass the old type, and then you get out of it a new type. So this is a more complicated pattern. So yeah, so this is how you would fill this array. So the block lengths array would be 1, 1, 2, 1, 2, 1, because these are 1, 1, 2, 1, 2, 1. And the displacements are the locations where the starting points of these blocks are. So they are at 0, 3, 5, 9, 13, 17 in that array. It's just detail. There is another function that was added in MPI 2.2, I think. So MPI 1, I mean, back in the day, just added this function, which took an array of block lengths and an array of displacements. It turns out that in some applications, the block length was a constant. So they did not want to create this array and then initialize all of those things to the same value. So what they asked for is a function where the blocks are of the same size, so you can pass it just as a single integer. It's only their index, the indices are different. So here there's only one array for the displacements, and this is a constant. So you'll notice that MPI is a comprehensive standard. It tries to have different variations of functions. It's not everything in one function. So it caters to different needs. All that does is it makes the standard a little bigger. The MPI 3 might be 800 pages, the spec now. But you can find what you need, and you should use what you need out of it. It doesn't add any performance penalty to the implementation or anything. And you don't need to look up all the functions. You can start with what you need for your application and then slowly build up. But everything is there, and particularly for library writers, who are sort of the advanced developers, they use all kinds of the complex functions and so forth. Okay, so that was indexed block. There's also an H indexed similar to the H vector. And the difference here is that the stride is, where is that? Yeah, the array of displacements is not in terms of units of the old type. It is in actual, in terms of actual byte offsets. So you might be familiar with the MPI A-int parameter. MPI A-int is an address-sized int. So if your address space is 8 byte, can be needs 8 bytes to represent it, then MPI A-int will be defined to be an 8-byte integer. Or if it's a 32-bit address space, then it'll be a 4-byte A-int. So the MPI implementation defines that in the MPI.h file, or in the Fortran MPI-f.h file, or in the Fortran module, in the MPI module, and so forth. Okay, yeah. So that was the indexed type. So what we have looked at so far is contiguous, where everything is packed together. Vector, where there's a uniform stride. And then indexed, where there is a variable stride that needs a vector to represent the stride in the first place. But in all of these, one thing that was common is that the data type that you passed is the same data type. So you cannot have different data types in a vector, or different data types in an indexed type. So this struct is the most general constructor, where even the data type can be different. So the data type is itself an array. So here you have a count, and then arrays of block lengths, an array of displacements, and an array of data types as well. So that can represent a struct. So for example, You can have a C structure with different types, an int or a float or something, and you can declare a struct that way. Or we had another example of a struct, which was, let me go back to that, which was here. You could declare something like this as a struct and then feed that to another vector type. So the struct is the most general, and it's useful to you only when you have different data types that you need to build something bigger out of. So let's say you have a contiguous type that you have created and a vector type that you have created, and you want to compose these two together into one thing, then you could call MPI struct with these different types. Okay? And there are also some convenience functions for sending array sections. So let's say you have a 3D array and you want to send one sub-array out of this to some other process. This is, by the way, quite useful in the MPI I/O part, the file I/O aspect of MPI, which will be covered next week. In the I/O portion is next week. This tends to be used more there than in MPI communication, but it can be used for communication. And the reason it gets used in I/O is because you could have a file containing your entire data structure, a 3D array, and each process gets some portion of that array, which is a small subarray of it. So how do you read and write that subarray from this big array? For that, you use the subarray type. So this is a convenience function in the sense that you could build it yourself using all these functions that I told you, the vector, indexed, and other things. It's just more work, and you could make a mistake in doing that. So what this provides is you can express this in terms of array notation. So you can specify the number of dimensions of your array, the sizes of each dimension, then the sizes of that subarray that you want to send, whatever is that little portion, what are its sizes in each dimension, and what is the starting coordinate of this array in each dimension. And the other parameter is this a C array or a Fortran array? Is this row major or column major? That's the question. So that's the other parameter you pass, and it's called MPI order C and MPI order Fortran are the two choices you have. So in terms of your array sizes and subsizes is how you specify it. And the old type is whatever this basic type. If it's double precision, you say MPI double or whatever. And then what you get back is a derived data type representing your subarray out of this that is built correctly for you. In fact, internally, it may be built using one of the functions we just looked at, because that's what it boils down to eventually. It's non-contiguous in some way that can be built, but if you try to do it yourself by hand, it gets a bit tedious, particularly for the 3 and 4 dimensional arrays. A 2D you can manage just using a vector type or something, but when it gets to 3, 4D, you have to do it a little carefully. So instead of that, this is provided for you. And there is another version of this called distributed array, where let's say you have an array that is distributed among processes in some way as a block distribution or a cyclic distribution. Then you can use this function to create it, as long as the definition of this matches exactly the definition of the distribution in your program. And where that comes into play is, let's say your array size is not exactly divisible by the number of processes in that dimension, then how is it divided? Is it a ceiling division or floor division? So you have to follow what this thing says. It says it's a ceiling division and so forth. So it's less useful, I think, than the previous one, because it may not match your application and then it will do something wrong. Whereas here, you can explicitly specify on a process which part of the subarray you want. And in some cases, for that, you might have to do some calculations to figure out what is the array, what is the starting index, and so forth. But you can do that, and it's less error prone than this one. But I just put it up there for completeness. So is this clear? The various data type functions, and what you can do is take the output of one function as an input to another data type function. So that's how you can build any complex layout that you can imagine can be built with these because you can recursively call these functions. And at the very end of the whole thing, you call MPI type commit, as I said, and it'll be on some other slide, where MPI type commit tells the implementation that you're done now creating your data type. You've specified what you want to specify. You can look at what I have. They're telling the implementation that you can look at what I have done, try to understand it so that when I do my communication, you can do that more efficiently. Yeah?
Just wanted to confirm, so is it always true that it's better to use a derived data type than actually copying the values into a buffer for yourself and then send the buffer?
It's not always true, and the reason has been that the MPI implementations have historically not optimized this feature as much as it could have been optimized. Although it has improved over the years, and there have been papers on how to implement data types efficiently. But the users have, in the past, have had not good experience with data types. They find that if they pack it themselves, it performs better. So many codes still do that. But I think, at least today, you should try using this first. And if it still doesn't perform well, complain to your MPI implementer, or your vendor, whoever is running on that machine, and get them to improve it. But at least for the simpler types, the vector type, or even some of the simpler index ones, I think you should try using the data type concept. Yeah.
Is it, assuming we are creating a very complex data type, I use vector and struct and then multiple layers, would there be a problem if I was committing all the initial data types also, because maybe I want to use them also explicitly?
Yeah, I don't think there's a problem. So if you call, say, a commit after each of these, it won't cause any harm. But there's unless you plan to use them separately, there's no need to do that either.
Yes, of course.
Yeah.
Thank you.
Yeah.
Is the cost sort of dependent on what kind of data you pack over there? Like, for example, if I have, I'm referring in particular, I might have an object in C++ in which I actually store different types, and I would like to create a data type for that one. If I have variation in what kind of objects, what kind of data I store in that object, is going to increase the cost, or it's actually pretty much, I mean, it doesn't matter.
So the cost depends on how easily the MPI implementation can understand what this data type represents. So I think I have let me just jump to that slide. So this is, it's the next one. So as we saw in this order of complexity, if you're closer to this side, it's easier for the MPI implementation to figure out what the data type is about. And the further you go here, and particularly if you have used some of these to create additional types, at some point the MPI implementation will just say, it's too complex for me to do. I'm just going to do simple copying, and then it will be similar to what you do by hand, basically the hand copy. So this is just some simple stuff. So let's say you use a struct data type where you have sort of explicit addresses of something in memory. So in that case, what is the buffer address that you pass to the MPI function, the buff count data type? So for that, MPI has a special value called MPI bottom that you pass, which actually represents the absolute zero address in the address space. So what this means is all your address information is explicitly provided in the data type that you have passed. You may not need to use this very often, it's just some detail. And then how do you actually get the addresses? There's a function called MPI get address that you can use in both C and Fortran to get the addresses. And this is useful in the MPI struct type mainly, not so much in the other types. I'd say it's just some detail that you probably won't need to use that much. So as I said, the types must be committed before use, and only the ones that are used. So the intermediate ones, you don't need to commit. And MPI type commit may perform some optimizations, and it might take some time. Some time means milliseconds or second. It's not very time intensive, but it's something that is done once, and then you don't incur that cost again, because you're just doing communication after that. And since you have created data types, you have called a function to create a data type. There is also a free function to free that data type when you're done with that. So that frees up resources or any internal memory that MPI may have allocated. There is also an MPI type dupe, which duplicates a data type, and that's typically used by libraries to create a duplicate of some data type that you may have passed to it. So this is similar to MPI com dupe for duplicating a communicator and so forth. Okay, there are other functions. So MPI also provides a function to pack and unpack. So you can pack a data type into a contiguous buffer, and similarly you can receive a packed type and unpack it into a buffer. And this was mainly provided back in 1994 for compatibility with other libraries that existed at that time and that had this kind of functionality. So this is not using data types for communication. This is for taking a non-contiguous buffer and packing it into a contiguous buffer and then unpacking it also if you want. And there are also functions for say, as I said, a data type is an opaque object. You don't know what's in it, right? If I give you a data type object, you don't know what it was. So if you're a library writer and you need to know what the data type is or how it was constructed, there are functions to unwrap, to call that will tell you how that data type was constructed, and they're called MPI type get envelope and type get contents, and that will give you the exact set of parameters that the user had called to create that data type in the first place. So that's more useful for library writers, I would say. I don't think, if you're just writing application code, you may not need to use that. And there is also a little more advanced function, I would say type create resized, that can change what is the size and extent of a data type. So that gets a little more technical about how, so when you call an MPI send on buff count data type, how does the replication happen? By replication, I mean, how does it take the second data type? Where does it take it from? So that is in terms of extent of the old type and so forth. Again, I would say you should just know that there is a way to change the extent of let's say you have a contiguous type and you want to add some blank space at the end, and you just skip some portion. So you can change sort of the extent of that type to include that blank space and make it non-contiguous in that form, and then that gets sent. But it's a more advanced use of MPI. Most users don't need to use that function. And I showed this slide earlier where the performance is better to the left, and as you go to the right, it gets more difficult for the MPI implementation to understand what the data type is, because it gets more general. Towards the left is more specific, so it's easier. Okay, I think that was just about, yeah.
Because you're mentioning performance, if you compare the buffering method with the data type,
yeah.
What about the memory impact? Because when you do the buffering, automatically you use more memory.
Yeah.
Okay. Is the same thing with the derived data types or not?
So it depends on how it's implemented. If the derived data type is internally doing some copying, it will also use some memory. It may not use as much memory as the whole buffer. It could do it in smaller pieces, and it could have a smaller buffer where it packs part of the data type into it and then sends it out. So, or on some networks where you can directly send strided data without copying it, there's no memory needed then, because you're just directly sending. So it's not clear. It depends on the implementation and platform and your specific data type created. But hopefully it won't take more memory than what you would have done by hand yourself. But sometimes the data type itself might take up some memory, because if you're creating one of these indexed types that take arrays as parameters, right? So that gets stored internally, that array gets stored. So if that is very large, that takes up some memory.
So it's the meta
Yeah, the metadata. In some cases, that might take up. Yeah.
So what about subarrays? Where do they come in?
Oh, yeah. So subarrays are here. So subarrays are, I would say, less than struct, somewhere in between indexed and struct is where they are. The 2D subarray would be easier. I think that gets closer to somewhere here. When it gets to 3 or 4D, it gets a little more interesting. Yeah.
Will the resize work with the index block also when we specify array for each?
Can you say that again?
Can the resize?
Yeah, so the resize works for anything. The resize, what it does is it just takes whatever data type you pass to it, and it changes the extent of that type. And I don't want to get into that. That gets a little more technical. And unless you have a good reason to do that and you understand the implications of that, it's to be avoided. It is like deliberately taking, let's say you have one integer, and which is of a size of 4. You can make it size of 8 if you want by changing the size of that. But then all your communication will happen in this new size of 8. So unless you really want to do that, you shouldn't do that. It's used in libraries, though, because libraries may be doing some fancier communication. And library writers are, I'd say, more expert or advanced users of MPI, so they tend to use that function. Yeah.
Is there a danger associated with using resize when the data type has already been sent out at some point?
When the data type is already, you're already doing a communication and then you do a resized on it?
Yeah, something like that. Or
So
like
when you do a resize, do you get a new data, the output is a new data type, right? Yeah, so then it won't affect the old one.